You may have to check your audio settings. Still can hear you. Not at all. So I think you need to go to Zoom settings and go to the audio section and check the mic you're using. Still can hear you. Are you using an external sound or a Bluetooth device? Can hear you. Check your audio. Can you hear me?
Yes. Good morning.
Yeah, good morning. I'm talking. Priya, can you hear me? Priya, we can hear you. We can hear your sound on Zoom. Label, please, can you confirm if she's muted? I don't
Uh,
think she's not
no,
muted.
yeah, she's not muted, but we can't hear anything. I think maybe the
Okay.
best thing that are they able to maybe to share their screen so that maybe we can help select the mic for them?
But if they are not muted, I believe they can share their screen. The problem is the microphone. This is something wrong. Can't hear you.
Of course, but we can maybe try help select the right mic or maybe another different one.
But you can do it. There's no way you can do it here if you can select mic for them.
So you actually once they start sharing the screen, I can get remote access to the thing, and then I can do that.
Okay, Priya, can you share your screen? Priya, can you share your screen?
he cannot hear.
तो उसमें लगा
नहीं मैं ये निकाली. I'm wondering whether देखो अब
Priya, I think you're back now. We can hear you.
now you can hear me. Okay.
Yeah,
नहीं,
perfect.
okay, fine. So we are ready. You tell me when to start and all's good. Right. नहीं Najam, I was wondering.
Priya, I think we can start whenever you guys are ready. We're just waiting for you.
We are ready. We are ready. So,
Okay, cool.
do we have share permissions?
You should have.
Yeah, just make me co-host or give me share permissions.
Okay.
which is a link.
Madam, there's morning and evening, na? Morning.
Yeah, you should have share now.
Okay. Okay, great. Okay. Yeah. Okay, shall we start? Madam, shall we start? Okay, let's start. Yeah. So good morning, everyone. I'm Priya Hassan.
We can see your screen yet, just to let you know.
I'm not sharing. At present, I just want to talk.
Okay, good.
No problem. Yeah. Yeah. So good morning, everyone. I'm Priya Hassan.
I'm Najmul Hassan.
Yeah.
And we'll be handling a little bit of statistics, though it has been done earlier. But we think it's important that we reiterate a few things, and then we get down to the visualization of astronomical data.
So we both teach at the university. We both teach at Maulana Azad National Urdu University, which is located in Hyderabad, India. And I teach physics and astronomy, while Najam teaches mathematics and astronomy. So welcome you all to our session. And we do hope that it will be interactive. Please do not hesitate in stopping us and asking us any questions you have while we are proceeding, right? So please do ask us questions if you have some, and we'd be happy to answer, right? So we'll start off with our first thing, which we plan to do. I hope you can see the screen well. Can you see statistical techniques for astronomy?
Yeah.
Right.
Yes,
So,
I can see.
yeah, so you can go on this one. Yeah. Yeah.
Yeah, so we'll be looking at a little bit of statistical techniques and visualization tools for astronomy.
Moment, please.
And
It's not going to beginning. This has gone to previous thing. One second, I'll just do it again. I'm sorry, this has gone a little bit ahead. Yeah, let's.
Yeah, so statistical techniques for astronomy. There has been a paradigm shift. There's a change in how people are looking at statistics. There's a changing perspective. Earlier, there's a Ernest Rutherford statement. He had said, if your experiment needs statistics, you ought to have done a better experiment. And there's this famous statement made by Albert Einstein, God does not play dice with the universe. Benjamin Disraeli said, lies, damned lies, and statistics. We have come to the realization that in the present era of rich data sets, it is essential to have sophisticated statistical techniques and methodologies to analyze and interpret data.
Is this? Yeah. Oh, sorry. I'm sorry. You'll have to repeat that. It is coming as.
Yeah, so I think I was muted, so I'll start again. Statistical techniques for astronomy. There's a change in the perspective of how statistics is being considered now. Earlier, people took statistics in a different way. Like Ernest Rutherford said, if your experiment needs statistics, you ought to have done a better experiment. Albert Einstein's famous quote, "God does not play dice with the universe." And Benjamin Disraeli said, "Lies, damn lies, and statistics." We have come to the realization that in the present era of rich data sets, it's essential to have sophisticated statistical techniques and methodologies to analyze and interpret data.
Sorry,
We don't hear you.
it's muted again.
Yeah, I don't know why it
Time and again it's getting muted. Statistics has changed meaning over centuries. Originally, it referred to collection and compilation of data. In the 19th century, it accrued the goal of mathematical interpretation of data. And contemporary statistics is an amalgam of science, technology, and art. Right? C.R. Rao states this in Statistics and Truth. This is how it's getting muted. Yeah, astronomy too has changed over years. It has gone from a data poor to data rich science. We live in an era of big astronomical surveys, like we have 2DF Galaxy Redshift Survey. Redshift surveys conducted by Anglo-Australian Observatory between 1997 to 2002. We have SDSS, Lone Digital Sky Survey. We have D2 Redshift Survey and 2 Mars Survey and Gaia. Gaia designed for astronomy, for astrometry. It gives positions, distances and motions of stars with unprecedented precision for about 1 billion stars.
So, the previous session, you all have seen some stuff with Gaia data.
Yeah.
Right?
And we'll be using Gaia data for our
Today also.
hands-on sessions too. So it has become essential for astronomers to handle the big data sets and interpret the complex astrophysical problems by using sophisticated statistical techniques and technology. We have 2 streams. One is the hypothesis-driven science and the other one is the data-driven science. In hypothesis-driven science, you have a hypothesis, you have a small amount of data, like it was so in astronomy earlier. Only they had a few observations, and on those few little data, they had hypothesized, they theorized, they conduct experiments, they analyze the data and try to understand the phenomena underlying beneath it. In the data-driven science, we have large data sets and streams. We have data exploration, from which we have pattern discovery. Then you set hypotheses, a theory on the basis of the data we have. We analyze data and we understand it. These 2 approaches are complementary. It's important to spend a little time on understanding what virtual observatories are. A virtual observatory is a collection of interoperating data, like archives and software tools, which utilizes the internet to form a scientific research environment in which astronomy research programs can be conducted. The main goal of virtual observatories is to allow transparent and distributed access to data available worldwide. It allows scientists to discover, access and analyze and combine nature and lab data from heterogeneous data collections in a user-friendly manner. The IVOA, which is the International Virtual Observatory Alliance, is a standards body created by the VO projects to develop and agree on the vital interoperability standards upon which VO implementations are constructed. They define certain protocols which specify the way data has to be shared and also develop some user-friendly ways of acquiring this data and analyzing it. Coming to statistics in astronomy, a lot of statistics is being used. I have listed out a few. For example, we use probability theory, we use time series analysis, we use ANOVA, the analysis of variance, correlation and regression is used, principal component analysis is used, clustering, hypothesis testing, point estimations for the use of analysis of modern astronomical data, least square methods, maximal likelihoods and Bayesian approaches to statistical inference, resampling, bootstrapping methods, and goodness of it. These are some of those which I've listed, and we'll be discussing a few as we proceed. Here there are two interesting scenarios. Question 1. We flip an unbiased coin 3 times. All 3 times, suppose we get heads. What would you expect in the next flip? And most of you would answer that the 4th one, since it's an unbiased coin and thrice heads has happened, you would expect tail should happen now. Otherwise, you'll start suspecting the coin. On the other hand, you have on the left side, you have a picture. These rocks have balanced for about 2,500 million years, and they have not fallen in 2,500 million years. Is it safe to stand under them? The question is, will it fall tomorrow if I go and stand under it? So here your logic goes in the reverse order, and the probability says that if it hasn't fallen for so many million years, that it's safe to stand under it, because and it won't fall tomorrow, right? It's counter to what we would have done in the question 1. Statistics is divided into 2 main branches. We have descriptive statistics, which basically is an analysis of data that helps us to describe, show and summarize data in a meaningful way. And the other one is the inferential statistics. It is used to make predictions by taking any group of data in which you are interested. For example, if you have a large population and you take a sample, a random sample of it, you understand the mean, the variance, and the trends in the small sample, and based on that, you understand the whole population. You infer. So this is the inferential statistics. Coming to statistics, there are 2 approaches to it. One is the Bayesian, and the other one is a non-Bayesian one, which is also called the frequentist statistics. Similarities: both forms of statistics use the likelihood function. Both forms of statistics are used for statistical inferences. Both forms of statistics can be used for data analysis and visualization. Bayesian statistics refers to statistical approach named after Reverend Thomas Bayes. He formulated a theorem that describes how to update probabilities based on new data. In a Bayesian framework, prior beliefs are represented as a probability distribution, which is the prior. New data is observed, and Bayes' theorem is applied to update the prior beliefs, yielding a posterior distribution. This approach is used in various fields, including machine learning, data sciences, and statistics. And the aim is of Bayesian approach is to update beliefs based on new data, make predictions, estimate model parameters, and perform model selection. For taking an example from astronomy, here's the problem. Suppose before 1987, 4 naked eye supernovae had been recorded in 10 centuries. What before 1987 was the probability of supernova happening in the 20th century? So the answers, there are 3 approaches to answering this. The first one could be people would say supernovae are physical events, in principle, can be accurately determined. They are not random events, and probability is meaningless. This is one approach to the issue. From the frequentist points of view, they would say in 10 centuries, 4 were observed, so the chance is 4 by 10. The assumption underlying here is supernovae were equally likely to be reported in the past 10 centuries, and hence the probability is 0.4. A priori arguments would say, in principle, we might know the stellar mass functions, the lifetime of a star as a function of mass and star formation rates in a galaxy, and the detection efficiency. Further take into account metallicity, obscuration due to dust, clouds, etc. And you can find the probability. Now I change the question a little more, and I say that before 1987 we had observed 4 supernovae in 10 centuries, and suppose now in 1987 another supernova is sighted. So how would the probabilities change? The first approach would say one supernova does not affect another. You can't predict it. The approach to the frequentist style would say revise the probability to 5 by 10, because now you have 5 in 10 centuries. And the approach 3 is will improve models with fresh data. Revisiting the same problem, we look at the Bayesian way of approaching it. It says you have 4 supernovae in 10 centuries, and a priori is a uniform between 0 and 1. And the distribution which we choose is binomial, because there are only 2 things which can happen. Either the supernova occurs or it doesn't occur. So there are 2 options, hence you use binomial distribution. And using binomial distribution, we calculate the probability of detecting with the given new data given. Okay, and it is proportional to 10C4. This rho is the uniform, is the a priori to the power of 4, and 1 minus 6, and we normalize it to 1, and we calculate this beta function, beta 5,7, which is gamma 10 by gamma 4 by gamma 14. Basically, gamma 10 is 9 factorial, gamma 4 is 3 factorial, and gamma 14 is this factorial, right? So if we use both the techniques, you can try it out by both the techniques. And here we have worked it out, and we see that the frequentist before 1987, it calculates to 32.97%, and after observing the next one, you get 36.5. So there is an increase in the likelihood of detecting supernovae in the, and the Bayesian approach gives us marginally different values. Instead of 32.97, we get 37.97 before in 87, and after detecting one more in 87, it goes from 36.5 to 40.7. And the key reason for this is the Bayesian approach gives a higher probabilities as it accounts for uncertainties in this parameter lambda. Both methods show increased probabilities after 97 observations. The frequentist method relies solely on observed frequencies, while Bayesian takes into account the uncertainties as well. Coming to principal component analysis, just a short brief slide on that. When there are many variables, the principal component analysis, the PCA method, is the best correlation searcher. Suppose we have a sample of n objects with n parameters. For example, the capital N is the number of, say there are 1,000 galaxies, and we have n parameters to it. For example, N could be 10 or 20 or whatever. So you have 1,000 objects and you have 10 parameters where you have the size of the galaxy, the morphology of the galaxy, the metallicity of the galaxy, and so on. So suppose you have n objects, capital N objects and small n parameters. PCA is used to find out what is correlated with what. You try to find correlations between that, and you try to find out what are the prime parameters which are actually affecting a certain thing. If you are interested in studying a certain aspect, say electricity of a galaxy, or you want to study some nature of spirals, we want to find out which variable produces the primary correlation, which parameter constitutes a secondary, and so on. So the task for the PCA is given a sample of n objects, capital N objects with n measured variables, say xn for each. We try to find a new set of xn variables that are orthogonal, and each one is a linear combination of the original variables with values. This is basically linear algebra with values aij's, such that the smallest number of new variables which account for the much of the variance as possible. These form the principal component, right? So we write these sigma i's in terms of the xj's with these functions, and you find the relation between that, and it gives you a relation and tells you which is the most important thing, which are the most important components which are necessary for the phenomena. So statistical data tools are many. One can use, just see the chat there.
Yeah. How long on stats?
SPSS, we have R is a open source tool. We have virtual observatory tools. We have Python. So
she thinks it's very advanced, this stats. Okay.
Yeah. So Python is something which we'll be using. And there are these virtual observatory tools. We have VO tables, VO plot, Topcat, Aladdin and Isaskai are used to display, analyze images. We have VO spec and spec view to analyze spectrum, to display spectrum and analyze it. Aladdin is a very useful Java applet which you can download from the net freely. And it is an interactive software atlas allowing the users to visualize digital astronomical images, superimpose entries from astronomical catalogs and databases. And we have CDS to access the data. And we have this Strasbourg Astronomical Data Center, CDS, which is a collection and distributes astronomical data, catalogs, observations of stars and galaxies, other galaxies, galactic objects, solar system bodies, and so on. So it's a large collection. Sinbad contains 20 million objects and so on. So we'll be sharing this PowerPoint which you can go through and look into all these services, Vizier, Sinbad, Aladdin, and so on. And these are tremendously useful software and online resources for astronomers. Data is a freely software which is supplied, where you can do statistical analysis. And there are various plotting tools like Topcat, Python, VO plot, and Stills, VO converter, and so on. So we'll be using mainly Python, and you'll be seeing in our hands-on session sets of this kind, where I think you have been introduced to pandas. We import pandas as PD. And there is something called Y data profiling, in which we import profile reports. And we use this Matplotlib in the hands-on sessions which follow now. You will be seeing this. We'll be using this to plot the data, to understand the data, because just a set of numbers does not give us much. And similarly, we have Seaborn libraries which give us very beautiful plots. And there are commands which are extremely simple. For example, in pandas, you can read comma-separated variables. You can download, say, DIAS 2018. We are reading as pd.read underscore CVS into data. And you can see the data, and commands like data.describe will give you the basic statistics of the whole data. And when you do the profiling of profile reports, it gives you all the basic data, the correlations between variables, regression analysis, and so on and so forth. So with this, we'll come to an end of this presentation, and we'll go on to the hands-on session.
Yeah. I hope you all found this interesting. The basic idea was that when you finally do analysis, you may need to use some of these. I can see that there are some questions. So let us first answer some of those questions. Yeah, where can we access recorded scripts of the seminar form? So I hope you know that it's all there on YouTube. There's a BRICS channel, BRICS Astronomy channel, and you'll be able to find it on YouTube. There's a question by Anubhav Datta. Is the equation of eta ij is equal to aij xi? Why aij is a tensor? Actually, this is not related to what we are talking about today, Anubhav. So you can probably send me this question on Slack and I can answer it. But we won't want to spend time on...
aij is not a tensor. Each sigma I is written in terms of xi's. So for each sigma I, you have this eta ij's, which you understand, it runs over. You will notice that eta I is summation aij xi, and the j xi is going from 1 to n, right? So for each j, you have a different. It's not a tensor. It's just a real number, right? So you are writing it as each new variable eta I is being written as a linear combination of xi's, right? It's not a tensor.
Yeah, and I'll answer the next question. Which is a better tool, Simbad or Vizier? So Simbad and Vizier are slightly different kinds of tools. So Simbad is, for example, if you have an object, I can show it to you, for example. If I will answer this question over here. Let me see it over here. Yeah. So I hope you can see my screen. And so Simbad, what happens, it's if you actually see it, that's CDS Simbad. It's basically a database for giving you query. So for example, if I query M51, okay, this is a galaxy, sorry, M50, okay, sorry, it got slightly wrongly typed. So if
Hi, Priya. Because of time, I think we should actually go into the visualization section, and then these questions will be answered later. Yes.
Yeah, so this is how Simbad works. It gives you the list of the object and the things. Vizier will give you direct access to the catalogs which are there sitting based on published papers, right? So you would actually have to use it in that way for that. Okay, so let's start with our first notebook. Okay, now you've been shared it on GitHub. So let's first start off with the Matplotlib notebook. This is the Seaborn one. Let me just upload my notebook. So please, everybody can open your Google Colab and upload the notebook on Matplotlib, right? Yeah. So I think last class you all have been slightly introduced to Matplotlib, but we'll obviously see it. So I hope you can see this thing. Has everybody opened their notebooks, right? And I hope you all are aware of how to use the Jupyter Notebook interface, right? So everybody, please open your notebooks, and I'll keep the Slack channel open for questions in case, or you could also ask questions directly here on on Zoom, right? If you have questions. So sir will keep track of the questions which you have on Zoom. So please put your questions there in case you have a problem. Okay. Okay, so we'll just refer to things which are pertaining to this. So the first thing, obviously, you have to do it in any of your notebooks is you need to import the necessary packages, the necessary libraries which you need. So for Matplotlib, that is the simplest plotting package which is available on Python. We generally say matplotlib.pyplot as PLT and import numpy as NP. So now what we are going to do is we are going to generate a data set which we are going to use for plotting, right? So I hope you are aware of, last time you'll have done NumPy. So we have X is an array which we are creating using NumPy, and we are using this thing called linspace, right? What does linspace do? Linspace is basically generating my data points in such a way that my data points are lying between 0 and 10, and I am getting 100 such points. So if you want, I can show over here. If I want to just look at X is this. So what has happened? I've gotten 100 data points which are placed between 0 and 10, and these by default are equally spaced. If I want the spacing to be different, I may have to put it in a different way. But at present, we have basically generated a data set which is a single array of X, which is 100 numbers between 0 and 10. So you can see that between 0 and 10 I've divided, and therefore you have 0.51, 1.52, etc. And in that way you are moving in steps of 0.5 so that you develop your this thing. Now we are generating another data set which is Y. So how are we generating Y? Y is exponent of X. So I'm just going to add another code cell to actually show you what Y looks at as. So you'll have, it'll be all these values of X to the to the power, right? So I will just put this, yeah. So you can see over here, I've actually put e to the power of all these values of X, which you can see are listed over here, which are showing you all your values. So what we've done is we've actually generated a data set of X and Y. If you remember, X lies between 0 and 10, 100 values equally spaced, while Y is e to the power of X, where X is given by that earlier data set, right? Which be this thing. So the simplest thing which you can do is what is called the plot function, the basic plot function, which is plt.plot xy, right? So this is the simplest plot. You can play around with this. What would you do if you need to change your, your limits, for example? You want to change the range of your limits. If you want to change various things. So I'm going to leave that to you for assignment. If you can actually try playing around with this and see whether you can, how do you change your these things. I hope you've also been introduced to what are called cheat sheets, okay? So if you actually, in the GitHub page, you have been provided with, I'll show you this, 1 minute. I'm going to show you the big three. Yeah. So if you actually see, another essential thing which would be nice for students to get introduced to is what are called cheat sheets. Okay. So everybody rather, I would say, who even is an expert Python user, we've been using Python for many, many years, you'd obviously not know everything, right? And therefore what is generally done is if you want to actually access it and get information, one way is obviously you can Google search, or you can use ChatGPT or things like that. But the other simpler way, which traditionally we used more often ourselves while we are working, are what are called cheat sheets. What are cheat sheets? Cheat sheets actually give you the details of all the all the commands you can use when you are this thing. For example, if you look at this, I will zoom this a little bit. No, this is not getting zoomed. Yeah. If you look over here, Matplotlib is basically based on NumPy. So the thing is that whatever you give to Matplotlib to plot should be preferably a NumPy array. Okay. We later on today also look at Seaborn. In Seaborn, it should be a pandas data frame, your data, the format of your data. So what happens is that when you are creating NumPy arrays, you will plot them with Matplotlib. But typically, if you're using Seaborn, you should have them as pandas data frames. I think you've already been introduced to pandas data frames, but you have to see that these get coupled with that like that. Now, what happens is, if you look at these cheat sheets, you can see here's the X value, here's the Y value. This is showing you how to plot it. There's not just one way of doing things in Python. You may do it in different ways. For example, I can define a figure to be a subplot, etc. These are subplots. For example, I don't want a single plot. I'll show that to you again. Supposing you want it as an array of plots, you can do them using subplots. I will not spend too much time on this, but you can see, for example, a plot like this. If I want it to be connected with a line, I'll say plot and it will do a line. But if I want only the points to be marked on it, I will call it a scatter. Okay. I can also define what are called bar plots and contour plots, etc. All these based on this. So the cheat sheet has been provided to you on the GitHub page. So please have a look at the cheat sheet also, because this gives you various things. For example, if you want to define the different kinds of lines, I'm doing this line, I want to see the line, and there are different line styles, right? For example, I may want a solid line, a dotted line, a dot dashed line. So you can actually have a look at this as to how can I have different kinds of lines. Or for example, if I want to, in my scatter plot, I want to have different kinds of markers, right? So the markers are also listed over here, the colors, etc. So it's a good idea to actually get used to referring to cheat sheets, like this one is a cheat sheet, which basically briefly has all the basic commands which are required for plotting, right? But we'll come back to this later. Okay, so here we saw was our simplest plot, which was our plot XY, where you plotted it in this way. Okay, I hope everything's going fine with this. I'm looking at the chat. Is there anybody having a problem with I'm sure everybody's managing this, right? Okay, so now the other thing is that you could try this out as an exercise. I've left space for you. So use the NumPy cheat sheet. There's another cheat sheet, which actually you can evaluate the function 7x plus 2 between 0 and 10. So you've already generated x, right? Now you can generate y to be 7x plus 2 and then make a plot of it, right? So I'm not going to write the code over here, but I'll leave that for you as to how would you actually do it. It's exactly the same way. Instead of having your e power x, you will put it as NumPy 10, whatever. You try it out. I don't want to say it. Okay, let's move to something more interesting. Let's look at trigonometric functions. You could also define something like y1, which is a cosine of x or a sine of x. And here you can see this is my function y1, which is cos of x, and you can plot this thing. I can also plot here a very simple plot. I can show you, which is the plot of x, which I have from 0 to 10. And then I plot it in terms of sine x. Please remember that Python always takes angles in terms of radians, right? And therefore you can see that here you'll approximately have your 3.1, your pi, 2 pi as your period. But typically if you want to convert it to degrees, you will need to do it like that. I can see there are lots of questions on the chat. Let me just open it and see it.
Hi, Priya. I think you should just continue. At the end, we can answer the question.
Okay.
Yes.
I mean, I suddenly saw there were like 7 questions. Okay. So this is the file called matplotlib.ipynb. That's right. Somebody has mentioned it here. Please check on the GitHub page. It's already there, right? Okay. Yeah. So what happens is so like you can look at this thing, you can add any number of plots to your plot just by adding the commands, and it will all be added onto the same plot. So you can see it's put, and by default, it selects a different color for each plot, for each line. If you want to change it, you'll have to change it using markers, but we'll come to that in a while. The other one is here I've made, you can also plot If you remember, one was sine x and one was cos x. If we come back over here, let's see, y1 was cos x and y2 was sine x. So for example, if I want to, there are different plot styles. I can actually use this, and here I'm plotting it for both, for sine x as well as for cos x. Okay. Now the other way is that, now let's get a little bit more complicated. You go on with the same plot, but you see that here there's a default setting which has come. If you remember, I spoke to you all what are called markers. Markers are the scatter plot, the point which is used for markers. So for example, you can see over here when I have x and y1, the marker is a circle, which is this circle over here, which is for the red one. I've put a line style none because I don't want a line. I want this plot to be only in terms of points, right? What are the points? The points are my 0 to 10, 100 points. I'm going to use those points, and I'm taking them and doing the cosine of those points, right? And therefore you can see that here when I have my cos of 0, I have it 1, right? And these are only in terms of marker points. These are not line, okay? So otherwise I would have to change my line style and give it a line. This is the label cosine, because cosine is what I've done for the red plot. The second plot is the one with y2, which is the one for sine. And here in this case, what I've done is we are doing this in terms with a line style, okay? We are not doing any markers. This is the line, which is the line style given by 2 dashes. So you can see that here I've put in the line style and I've put in 2 dashes. So the cosine plot is basically with markers, which are giving me circles, while the sine plot is basically with this dashed line, which is the blue line you can see over here. There's also, you can also give parameters called color. You can actually see all the different parameters which can come for plot, right? And you can either use it over here and see it. You can look over here, you can see define plot. It has various arguments, and you can actually give that all the different values. You can see over here when you're plotting it, it's giving you examples also. You can also, for example, change the line width. Okay, supposing if you want it to be thicker, or for example, you want a certain color, you can actually change the thickness and change the color and do various other things. For example, this is a blue circle. This is a green circle. For example, I'm doing 2 plots where I have a blue circle and a green circle. I'll say this, and I can change it in that way. So you'll see that when you put a tab over here and you give this, it by self, you don't even need to look at your cheat sheets. You can directly see it from the prompt over here and see the various parameters. So you have x, y as the scalar, and then you can change all these other parameters. They are all listed because there are a whole lot of parameters which can be adjusted, which can be given, which can be used for this purpose, right? So what you can do is, it's just a question of trying it out a few times as to what are the different parameters that you need to change and which you want to do. And it obviously happens as per your requirement. Whatever's your use, you may actually change whatever ones you want. Like I mentioned to you, the input is always taken in radians. If you want to convert it to degrees, you will have to physically multiply it and do it like this. And okay.
Jatin wanted randomly distributed data, send him a file.
Okay. Okay, fine. So this is your plot over here, which is giving you this, right? Okay, that's fine. So now here, for example, we are looking at another, so I hope this makes you clear how do you make a scatter plot and how do you make a line plot and how do you change all the parameters you may want to change in either of the 2 plots. You take Seaborn then. Okay. So now what happens is we're coming to the next one. In the next one, what we are doing, this is the same one which we did actually. This is the line and the cosine. Supposing you have a graph for 2 functions, okay? For example, I have f1, which is sine x, and f2 is 2 sine x cos x, that is sine 2x, right? So let's say we are doing this over here, and you make a plot like this. Make f1 to be dashed and make f2 to be thicker. So since you'll already have the Python notebooks, I'll give you all a minute to try it out. I think maybe that would be a good idea. I don't know. You can try this out. It's just very, very simple. You already have the code over here. So often you just cut paste the code and you can put it over here. First of all, define f1x, define f2x, and then you can actually cut paste this code and put it over here and see how to do it, right? So please try it out and see whether it works out easily or no for you. And right, I hope that's coming fine. All right. So I'm going to proceed. You can also, for example, you can, for example, here I have another thing. If you want to create a new figure, you could also create plot figure. And these have different methods actually. We'll come to later on part of saving it, but you can put your plot, PLT plot. We've done this before. So in this, what is happening is now this is separating my two plots into two different files, into two different plots. So I don't want, supposing I don't want an overplot. This is overplotting on the same plot. Supposing I don't want an overplot, then I will have to say plot figure, and then I say again PLT plot. So now you can see both my plots have come in two different figures. They've not come in the same figure. They've been separated, right? Another way what one can do is what I was talking to you a little bit about when we spoke about cheat sheets was what are called subplots. Okay, subplots are very often used in analysis. This is basically if you have an array, like a matrix of plots, right? You don't want to do a single plot, you want to do more than one plots. So these are called subplots. So let's say, for example, I have a figure which is axis, which is PLT subplots, and I define it as that. Now what is done over here, I can therefore then define each plot which I want. For example, my first plot is x with y1. I can give it whatever labels I want, which you can see. For example, the label is cosine. I can say my location, where do I want it, on the lower right, for example, or lower left, whatever area you want it in. I can set an X label, a Y label, and a PLT show. So then it finally plots the plot, and you can see that this is the one with this thing. So if, for example, I want to do many plots, let's say I want to do 4 plots, like in this case, I will say fig axis, PLT subplots, 2, 2. So what is this basically doing? It's doing 2 by 2 plots. That means 2 in X, 2 in Y, totally 4 plots, right? So this works out very well, especially while doing analysis and all that. If you want to demonstrate something, this is a very useful tool you will do. And basically what you're doing is you need to be a little, notice this a little carefully, that your numbering starts from here. You can see this is 0, okay? So the 0, 0 plot is the exponent plot, which is this one. This is your origin, okay? Now my squared plot, you can see, is my 1, 0. So I am continuing with, this is 0, so this is 1. But this is column number 0, okay? So this is basically your rows and columns are starting from 0, 0. So 0, 0 is this. And then when I do, for example, 1, 0, my row has increased by 1, but column is still 0. So therefore this is squared. Then when I want to do cosine, cosine is 0, 1. So it is the 0th column, but it is the 0th row, but the first column. And therefore that's the cosine file. And so cosine plot, sorry. And the sine plot is the 1, 1 because it is row number 1 and column number 1. Remember, we are starting the counting from 0, 0, right? So this is 0, 1 in terms of rows, and this is 0, 1 in terms of columns, right? So therefore, what happens with this way, I can very comfortably define all my subplots. And then you can use exactly the commands which we used here, for example, in the earlier case, where you can adjust your markers or your line styles or your line thickness or whatever other parameters you want to change for each plot. You will change it accordingly when you're putting it in terms of these subplots. Okay, so that's how you'll do it, like that. And you can always, all these things, they will be defined as, for example, when I'm putting this, I want to put a label. The 0, 0 plot is this one, obviously. I've put the label called exponent. The 1, 1 plot will be this one, which is the sine plot. The 0, 1 plot will be this one, which is the cosine one, and this. So you can see that I can actually add my legends to my various columns and get it in that way, right? So I've given you a small job over here to do. Define 100 equally spaced points using linspace. We've already done that earlier. Now, how would you actually define random points, right? So earlier what I showed you was if you want to actually have equally spaced, so that was linspace 0, 10 with 100. How would you actually do it with random points? So I would encourage you to see that it's just np.rand, that is the random number generator. But the random number generator actually defines random numbers between 0 and 1. Okay, so you have to actually multiply that into whatever number you want. For example, if you want it ranging from 0 to 10, not 0 to 1, then you have to multiply that into 10 so that you generate numbers between 0 and 10. Okay, so you can try that out, generate 100 random numbers, and then you can save it, and then you can define your y, for example, and define it like that. So Daniel, should I be giving people time to try out these things, or should we move to Seaborn?
No, you need to move to Seaborn.
Move to Seaborn.
Yes.
Okay, so we'll do
Yes,
Seaborn.
and you should do a little bit of that statistics notebook and then.
Daniel, we also have that stats notebook which we gave you. Should we do that, or we'll first do Seaborn? Let's finish Seaborn.
Oh, no. I think let's focus on the visualization because
Okay.
they've shared it there so they can go look at it.
Okay, no problem. So I'll now open, please everyone open the Seaborn notebook that has been given to you in this thing. I'll just do that. Okay, 1 minute. Please open this. You can use this matter.
Good.
You want to receive now?
Okay.
Okay, so let's now look at the Seaborn tutorial. So like I told you, what happens is Matplotlib is actually I want to reduce this one. Where do I choose? Okay. So what you can actually do is, like I told you, when you're giving data to Matplotlib, it is basically in the simplest form, so it's a NumPy array. Seaborn is actually a data visualization library which is built on top of Matplotlib, okay? And it actually, in principle, Seaborn creates much better visuals than Matplotlib, okay? We'll talk about that also in a short while, but let's just see the basic thing. But what happens is you need to give in your data to Seaborn in the form of pandas data frames, okay? Not NumPy arrays. And therefore, and that actually makes it much more convenient because actually NumPy arrays are much more easy to handle. Okay, so we've also given you a data file which is m3.csv. So in Google Colab, I'll show you how do you upload data files. So click on this folder thing over here, right? And here you can see there's an upload button over here. So I can upload, and I'm going to upload, it's not here, I'll just do it. m3.csv. You all have this file with you all in the GitHub page, okay? So please use that. And you can see over here, I've uploaded this data file, which is m3.csv. M3 is a globular cluster, okay? And this is basically Gaia data, which is in the format of comma separated variables. That means between each number, I have a comma which actually separates the thing. So this is called the CSV format, which is a very simple format to use because you can open it even with an Excel file or with Excel or whatever. You can even visually see it. So it's a very convenient format to have. Okay. So here what I'm going to do is, again, I'm going to import, and you can actually, installing Seaborn is not difficult, but I think it's if you don't have it, you'll have to pip install Seaborn, okay? And if you have it, I think Google Colab has it, so you don't have to worry about it. You can just import. So I'm importing NumPy, I'm importing pandas, I'm importing Matplotlib as well as Seaborn. Now I wanted to just say that these short forms, right, with which we import it, these are kind of standard, okay? So typically, it's a standard to import Seaborn as SNS, okay? It is not imported as C, right? So people generally follow that same convention when you're importing libraries, okay? There are standard ways of importing it, and it's better to stick to that one, okay? So first thing what we are doing is we are going to import the data which we've just uploaded. So you can see you have CS data frame, which is it's reading this CSV file in pandas. I think pandas was introduced to you in last class. So you know pandas is PD, and I'm saying pd.read CSV, m3 CSV. So we are basically looking at that file. If you want, I can actually show you what it looks like. you all have already been introduced to Gaia data. And if you want to see the head, you can, okay, let us see the head. If you want to see the head, it will just give you the top of it. So you can see that this, it's a very small file, which is basically giving you only some parameters for Gaia data, which is 4 stars, you're getting the RA, you're getting the deck, you're getting the parallax, proper motion in RA, and proper motion in deck. You can also, for example, let's see how long the file is. I can see the len.csv and okay, len.csdf. Okay, so we're going to look at the length. It's not a very, it's 36,000 points which we have approximately, and this is the basic data set, right, which is this 36,000 lines which are giving you these parameters. Okay, you have been told a little bit about Gaia, so I will not spend more time on it because I would love to talk about Gaia. So what we are going to do is we are going to make a very simple plot just now, the first plot, and you can see the power of Seaborn with this, where you can see that you have a column which is called deck. Okay, these are the astronomy coordinates, RA and deck. So it's basically taking the deck coordinate and it is plotting it. Okay, if you look at this, we are doing plotting. This is the parameter which we are doing it, which is doing with deck. Distribution plot, we are seeing the distribution, and this is called the kernel density estimator. Okay, we've said true and we've said the number of bins we want is 25. So here I have my 25 bins, and you can see, so this is given me, on the one hand it's a histogram plot also, and it's also given me this fit, okay, the KD fit which it has for these, or for the deck, right? You could change this to any other parameter which you want, which you can see in this file. You have RA, you have deck, parallax, etc. So I can, for example, even change this in terms of RA if I wish, and I can see the distribution which is coming for RA, right? I can see it's a nice smooth distribution. Why is it smooth? Can anybody answer that? Why is it smooth? Because I've basically done a cone search in looking for sources in this certain region, which is the region of the globular cluster M3, right? And therefore, obviously, the number of stars will obviously fall in that way because I'm selecting it like that. Proper motion RA, on the other hand, you can see is not exactly being fit like this, right? So how would I adjust this? This you can try with it yourself. Here is my thing. I want to what? I may increase my number of bins. I may want to change my range. How will I change my range? Please have a look at it. Again, I will show you what has been provided to you. You have been provided with a cheat sheet also for Seaborn, right? In the good old days when we didn't all the time Google for things, we often used our cheat sheets, and the cheat sheets give you various other parameters. For example, the data, or how can I make my my figure look more aesthetic, or for example, the different plots, etc. How do I choose different parameters? So you can have a look at this also, which is provided to you on the GitHub page, which is called Seaborn Cheat Sheet or JPEG. So typically what traditionally we always did is, instead of, everything, you can't be using ChatGPT or, Meta AI, for example. If you have your cheat sheets, for example, for NumPy, for Matplotlib, for Seaborn, etc., these were very useful things to use so that you can directly access and, plot your things without requiring much help from outside. Okay. So I won't go into more detail with this, but you can look at parameters and check it out like that. Now we're going to do something which is very interesting, which is called a joint plot. Okay, what is the joint plot? I am plotting RA versus deck. So it's like a scatter plot only. But what you can see is, look at this, it's such a beautiful plot. These are all the stars within that region which has M3. These are all the dots over here. What it's done is it has plotted the scatter plot, and at the same time, it has also, if you see over here, the kind I've said is this, and it does the KD, and I can actually see the distribution in RA. This is the RA, which is the x-axis, and I can see the distribution in terms of deck. It's a very beautiful plot, very useful kind of plot to have. You could also, for example, do a KD plot, which if I do not want the bar graph, for example, which I showed you earlier, I can just directly have a KD, which gives me the the kernel density estimator plot for RA, for example. I may do a similar one for DEC. And exactly these are the plots which you're seeing on these sides, but with the bars, right? There are different ways of changing parameters over here with which you can adjust it in whichever way you want. I won't go into those details, but you can try that out yourself. Okay, so this is a very useful thing to do. Okay, a joint plot, a very useful plot to do. Another very, very useful plot to do is what are called pair plots. Okay, now if you see in our data set, we had 5 columns. Okay, RA, DEC, proper motion RA, proper motion DEC, and parallax. Okay, now I want to look at the first hand to see whether there is a relationship between these parameters. Okay, and therefore what we'll do is I'm going to plot everything versus everything. Okay, so this gives you a kind of a matrix. Okay, we'll have a look at this plot. Just give it a minute to this thing. So like I said, you have 5 columns. So you're going to plot one versus, yeah, let's look at the plot over here. So you see we had RA, we have DEC, we have parallax, proper motion RA, proper motion DEC. Similarly, have the same ones on the x-axis, RA, DEC, parallax, proper motion RA, proper motion DEC. So it's a symmetrical plot. What it basically does is on the diagonal, it gives you the KDE. Okay, it gives you the distribution of each of the parameters, which is there on your diagonal. On this, what it basically does is you see the first column was RA, and therefore it plots it versus the second row, which is DEC. So this is RA versus DEC, this is the plot of the distribution. This one will again continue to be RA, but this is RA versus parallax. Okay, so you can clearly see that the stars seem to be distributed in RA, but you can see that there is a kind of this thing with parallax. Okay, and you can see that the bulk of stars are all centered around 0. Okay, this is an important thing which basically tells you that if you look at any region of the sky, the number of stars which are foreground and background are approximately equal, right? So we won't go into details, but Gaia data analysis, it goes through a pipeline due to which you actually even have negative parallaxes. Ideally speaking, obviously there's nothing, negative parallax does not make any sense because 1 upon parallax is distance. So ideally speaking, you should not be having negative parallaxes, but these are created basically because of the pipeline which Gaia data goes through. That's why you have that. We on some other time talk about how do we handle it. But in short, you get negative and positive, and you can see it like this. Now here again, you have RA versus proper motion RA. This is the plot, and this is RA versus proper motion DEC. So similarly, depending upon the position, this one is going to be the second column. So this is DEC, but it's the first row, therefore it's RA. So this is RA versus DEC, the same plot as this. Here I'm going to get, this is the first column, which is this is RA DEC, this is proper motion RA versus RA, right? And therefore what you can see is that we have a symmetrical plot. I will show it to you like this, you can see it better. You can see we have a symmetrical plot. The diagonal is the distribution and this. Now this kind of a plot is basically used to get a first-hand, a very important step to be done in astronomy when you get data is what is called data exploration, right? So last time when you had class, you spoke about mean median mode, for example, or the basic characteristics of the data because you want to study the data, right? And while you do that, another very simple thing to do is what are called pair plots, because you basically want to look for a relationship between the parameters. So if you remember, we are looking at 5 columns in Gaia data, and what I would like to see is there a relationship between column 1 and column 2, right? So I spoke to you also about what was called principal component analysis. What is principal component analysis? Is, for example, if I have 10 columns, supposing, of data, right? Supposing column 4 is a function of column 2 and 3, right? Then my column 4 is not of importance, right? Because it's basically a combination of column 2 and column 3. So when we do principal component analysis, what we basically do is, it is like what we call in linear algebra looking for basis vectors. You are basically looking for the columns which are important. You do not want to study the columns which are not important, right? And therefore what happens is you basically would like to only reduce your data to the important columns which are independent of each other, so that you can then look for, you can use them to do analysis. You don't want to use 100 columns of which 50 of them are generated from the other 50, right? So one very simple way of doing that is by doing pair plots. So when you do pair plots, for example, if you look at these ones, in this case, for this data set, we already know that there is no column which is a function of another column. All of them are independent things. RA, dec, parallax, proper motion RA, proper motion dec, they're all independent. And therefore you can see clearly in the plot that you're not getting any straight line regression. You already did regression last time. You're not seeing any kind of regression plot. There's no dependence, right? And therefore now in these pair plots, you can clearly see that all your 5 columns are independent. This is very important because before you proceed with your data, studying so many columns and so many complicated things, it's better if you know whether it makes sense to do that or no, right? If they are dependent, then you do not do that. You first reduce the number of columns you're going to study, and then you'll worry about how to, whatever you're going to do with it. Okay, so I'm going to go ahead with this thing. I hope this is clear. So pair plots, like I said, is also a very important thing to do. Now I'm going to slightly move from this thing, and I'm going to basically move to something, another data set, which is called tips. Okay. Now Python comes packaged with some data sets, okay, which are given to you specially so that you can use them for analysis in case you have some, just to do some basic tasks. Okay. Okay. Some people are having problems about this thing. The notebooks, they are all, look at the updated GitHub page and you'll find it on that. I'm sorry that some of the notebooks I sent them a little late, so therefore they just came later on. Okay. So here is this other data set which is there on Python, which is called tips. Okay. The tips data set is basically a data set which is basically the bills from a restaurant. Okay. Where the data is the total bill. This is the tip which was paid to the person. This is the one who paid it. Okay, whether the person was a smoker or no, what day of the week it is, what time was it, lunch, dinner, this thing, and what was the size of the group. So basically, this is just if you remember what Sir was telling you, that in the newer, modern, more contemporary kind of astronomy, we do less of hypothesis-driven astronomy. We do more of data-driven astronomy, right? You may have heard about data-driven astronomy. So what we basically try to do is we have data of objects, right? And then we try to study the characteristics of objects. For example, if we were to observe that in a catalog of galaxies, you see as redshift increases, supposing you were to see that as redshift increases, the number of spiral galaxies increases, right? Then you're obviously, that would give you a hint that as redshift increases, spiral galaxies increase, for example, or elliptical galaxies increase. And based on that, you would make a hypothesis of galaxy evolution as to why and how do the number of galaxies increase, spiral galaxies increase, for example, with redshift, right? So whatever model you make for the evolution of galaxies, that would have to take this into consideration. Okay, so typically what the kind of astronomy we do today, nowadays, is to a very strong extent data driven. That means when we have the data, we try to use that to get some correlation, some patterns, right? And those very patterns is what we actually use to try to understand or develop some kind of a theory, right? That is the basic purpose, that we can use it to do that, right? Now, what we'll actually see is that we try to, so for example, here in this data set, we are trying to see that, is it that people are given larger tips if people go on weekends for dinner, for example? Do they give more tips when it is dinner or when it's lunch? Or the person who gives the pay, is it a woman or a man? Do they give larger tips? Or is it when they are in a bigger group, that then they give a bigger tip because they are in a bigger group? Or is it vice versa? It could be like that. So here we are going to use this data set to look at that, and you are going to help me give some inferences about the data. Okay, so you can see this is 244 rows, 7 columns. This is our data set, and we are trying to see whether our data, does it give us the information we are looking for? Does it answer the questions we were talking about, right? So the first thing I'm going to do is what we did earlier, is we'll make a pair plot. What are we going to do with a pair plot? I am going to plot, you remember our columns, here I am plotting, we are plotting the, but we've actually said that we are going a pair plot, only we're changing it with different male and female, okay? So we are doing the total bill, the tip and the size of the group, and we are looking on whether it is larger when it is males or it is females, right? So the light blue is for males and the dark blue is for females. So the idea is we want to look and see whether is it that males give larger tips or females give larger tips. So here you can see this is the total bill, and I'm also plotting it taking these things into consideration. Is the tip larger? Ideally speaking, your tip has to be 10% of your total bill, right? So you can see that very well over here, that obviously the tip seems to be a function of the total bill, right? You can see that this is the tip and here's the total bill. So you can see that clearly if the bill is more, the tip is more, right? Which makes sense because there is a linear relationship between the tip and the bill. Ideally speaking, you should be paying 10% of the bill as a tip, right? So you can clearly see that there is a linear regression, right? You could fit this to a straight line, right? Which is the 10% thing which you could have. But you can see that there's a scatter, right? There's a scatter. It seems to be that men more strongly seem to stick to this linear regression, this formula, where they give a larger tip for this thing. But actually the problem is we even have larger tips with males. Okay, we are actually seeing that. But with females, you can see that it's kind of flattening. Probably after a certain point, they do not pay a larger bill for whatever reason it is. This is showing you how does the tip change with, for example, here your tip is changing with the size of the group, and whether the tip is increasing by that or no. And here are the, like we did in the earlier one, you can see the distributions of the total bill, the tip and the size, right? So another so you can actually use this to get so you can see that there is a relationship between the tip and the total amount of bill, but I would not say, would you say there's a distinction between size and total bill? It's not exactly, not as good as that, right? So it doesn't mean that if people go in larger groups, they give bigger tips. It's not exactly very visible. But obviously size and total bill, obviously these things, that if your size is more, your bill will increase. Okay. The other thing is rug plots. This is a very interesting thing. In a rug plot, it actually looks like a rug. But in this, what happens is that each individual point gets plotted. Okay. So you can see that you have a single column which has all the data points. Okay. These are all sticks on the axis. So you can see it like this. And it basically gives you a good idea of what is the distribution. Okay. So you'll see a dense number of plots where the amount is more or less common, etc. So this is basically called a rug plot. Okay. Which you have it like this. And you can do rug plots of the various parameters. For example, this is the rug plot of the tip. For example, here I have a rug plot of this parallax. If you remember the earlier KDE also, which we did of parallax, you can actually see that the distribution, oh no, I think I removed it, but you'll see that the distribution of the parallax is centered around 0, right? And then you have almost equal number on the left and right of it, right? This I told you was basically the way in which the data analysis is done, due to which this happens, right? Again, with a very important thing to tell students is that it is very important to make your plots look beautiful, okay? It should not be, what do you say, undermined that making a beautiful plot is useless. No, a beautiful plot can convey very well the point that you want to convey, right? So if you appropriately choose the colors or the markers or the various things in your plot, then your plot will very nicely convey what you wanted to convey, right? For example, even if you have a linear regression, I want this to look differently. It is not a right thing, but people also, they play around, for example, with the range. I may keep a larger range over here so that I can see this is slightly stretched on the x-axis, right? So if I, for example, increase the range of the x-axis, these points will come closer, and my linear regression or whatever linear fit may look even nicer and more convincing to the reader than it actually is, right? So actually people even play around with it in this way. So for example, if you look at this plot, I could actually increase the x range so that this thing seems to be less stretched on x, right? Because it has got quite stretched over here on x. I may accordingly play around. So that is not the fair way of doing it, but there are many fair ways also of doing it where you can actually use your plot to convey very beautifully whatever you want to convey, right? So that is how plots have to be used very, very effectively, you have to spend a lot of effort on how well your plot can convey what you would like it to convey, right? So styling of plots is something very, very important. And I'll show you very soon how to style it, not just like this, but in other ways also, right? So you can actually see this, and this was we've already done this kind of a plot. This is the pair plot, which is RA versus DEC. But this is, okay, this is our, this is the old one. Okay, fine. You can also plot things like bar plots. For example, I want to make a plot. I want to see whether the total bill is a function of the sex, right? Is it that men have larger bills or women have larger bills? And what I see over here, that males seem to have larger bills than females. Maybe, I don't know what is the reason, but there seems to be a difference in the total bill, right? Which is paid by men or women. Similarly, you could also have this thing on the, this is actually using our Gaia data. We are doing a count plot. This is also a very useful kind of plot. I'm basically trying to do a count plot of the parameter parallax. I'm sorry I'm going forth between this and that, but some of them are more effective or better with this. You can do it. I can convert it to also, to tips or whatever else I would like to do. I don't know why this is slow, but it's still doing it. Okay. Let me do a count plot even with sex. We are now doing it for our tips DF. I don't know why this is again going a little slow. Okay. Why is it doing it so slowly? I don't know. Okay, now it's going to plot it. I'm sorry for the delay, but some of you all must be trying to do it. And
should we do this one?
Wait, I'll finish. But I'll finish this. No, I'll finish this. Okay, I don't know why it's taking time, but it'll come in a minute. You could also plot it, the box plots. This is a very interesting thing to be done with box plots because, for example, if I have a distribution, I'm looking at if you see over here, I'm plotting day versus total bill. I don't know why is this taking time. Yeah. Why is it taking so much time to do it? I'm sorry, I don't know why is it this thing. But these are very important plots. This is called a box plot. And I also have what is called a violin plot. Okay. I'm also going to show you a violin plot. This is also a very important kind of a plot. Let's say I have a distribution. Okay. I have a distribution, for example, in this case of parallax. Okay. Or I have it of proper motion RA, proper motion DEX, right? I basically want to know how is my value distributed, okay? We'll be showing you this very soon in another notebook also, where I can actually use my box plot to give you the median values. It can give you the minimum and maximum, and it can also show me my first and third quartile, okay? I hope you'll have been introduced to what are called quartiles, okay? For example, supposing if I put my whole data set in ascending order, okay? If I put it all in ascending order, the first 25%, oh wow, it's all come. So good. So here you can see, this is a count plot, something's wrong. Okay, let's go to count plot of, for example, sex. This is showing me for my data set, which I had shown you, what were the numbers which I have of male data and female data. So I can see the amount of males are close to 160 and the amount of females are close to 80, whatever, you can check it exactly and get the numbers. Okay, so I know how my data set is. This is the one I was talking to you about, box plot. This is another very interesting plot. Look at this plot over here. If you see, I've done box plot and I've done hue sex. So hue is basically giving me two different colors. Hue is used to categorize the data. Okay, supposing I want to categorize the data, I may put it into two categories, for example, male and female. So it's chosen it from the column called sex. It knows there are two types. If there were three types, it would have put it as three. It's done male and female. Male is blue and female is orange. Okay. Now what it has done is it is actually made a plot over here. You can see it is day versus total bill. I am trying to study whether the total bill is larger on weekdays or weekends or close to weekends or whatever, right? There could be that people go to restaurants more on weekends because it's a holiday, or there could be that people go to restaurants more on weekdays because they have work and they want to, do not want to cook on those days. So let us answer the question. Look at this over here. This is Thursday, this is Friday, Saturday and Sunday. So actually it's difficult to find a pattern like this, but obviously in this plot you can see that people seem to go out more to restaurants on Thursdays, on Friday, Saturday, Sunday, right? Friday, Saturday, Sunday are the days when people have larger total bills than on Thursday, right? So this would also be that maybe on weekends they go in bigger groups, hence the bill is bigger, and maybe on weekdays smaller groups go and they do it like that. Now basically this is important because here this is giving you the mean, right? The center of it. This is giving you the maximum. This is giving you the minimum. So you see this is not symmetric, okay? This is not symmetric. This is the minimum, this is the maximum. And then you remember I told you about first and third quartile. So that means I put the total bill in ascending order, okay? And then I look for the first 25 and then I look for the last 25, that is over 75. So these are my first quartile and my third quartile. So these are the marks for the first quartile, this is the mark for the third quartile, okay? And then there comes the interesting part, which are these dots. I wonder whether you can guess, but these dots are what are called outliers. They are not fitting in this range, okay? Now outliers, they could be wrong data points, right? It could be that they're wrong data points, there's some mistake in the data and hence they were outliers. But in astronomy, agreed, it can be wrong data, but in astronomy, if the data is not wrong, then outliers are very interesting objects, okay? For example, you have an object with a very large proper motion array or a proper motion deck. That means it's a star which has a very large velocity, okay? So obviously the object becomes very interesting, right? Because you want to know why does this object have a large velocity. Typically an object with a large velocity is an object which is very close to us, right? So if you have an asteroid, for example, which is coming to the Earth, right? Its velocity is going to be very large compared to the velocity of the background stars, okay? So this is, therefore, it's an outlier object, but it's an interesting object because it is the asteroid or whatever, which is moving at a very large velocity, right? And therefore, I may find it very interesting to actually study these outliers. So often you could have a study that, for example, you study all your objects and the ones which fit into these boxes are not the interesting ones, right? Because they are the ones which are following the pattern. The interesting objects instead are these outliers which are sitting over here in these dots, which have larger or lesser values of the thing. So box plots are therefore very, very interesting and important for what is called data exploration. When you're exploring your data, if you're trying to check how is your data distributed, what are your outliers, what are your things, you can use this. Another improvement of a box plot is what is called a violin plot, okay? The violin plot you can see over here is exactly the same. See here, this one is day total bill use X. This is exactly the same thing. It's using the same data set, day total bill with hue sex. Only difference is that what it's doing is that it's giving you a nice distribution. This is the one for males on Thursdays. This is how it gets distributed. This is how it gets distributed for females. So obviously, therefore, it's not a symmetric plot. Here is the distribution on Fridays for the bills that men pay. This is the distribution that females pay. This is men, women on different days. So a violin plot now, if you look at it, it is actually conveying a lot more data than this one is. I mean, it obviously depends upon what do you want it to convey. These ones are neater plots which show you the mean. It shows you minimum, maximum, first quartile, third quartile. This one is instead showing you the distribution. How does it get distributed? For example, I know on Thursday it's somewhere around, let's say, 18, and it is somewhere for men and somewhere around 15 for women. But for example, I can see, so you can almost see that for men, the average is quite similar. Here on Fridays, it's a little lesser, but about the same on Thursdays, on Saturdays and Sundays. On the other hand, for women, if you see, the bill is this much on a Thursday, similar on a Friday. On a Saturday, it's kind of flatter, and on a Sunday, it's actually kind of, it's lesser, right? The peak is coming here. So violin plots are very, it's a combination of box plot and KDA, and it very well gives you this distribution. So it depends upon what is your purpose, whether you prefer the box plot or whether you prefer the violin plot. The strip plot is another plot which is similar to this kind of a plot. Again, it is categorized. Blue is men, this thing. It's exactly the same data set, day, total bill, and then this thing. Only that you can see it's putting here, it's even more well showing you the density of points. Where do I have more points, right? Compared to this thing. So for example, here when you're seeing it, you see it like this, but here you can nicely see the data points. So you can see that women do not seem to go out too much on Fridays. Your data points are less, while your density is different. On Sundays, for example, a lot of men are out. Saturdays, Sundays, you have lots of men out, lesser men out on Fridays, and then on Thursdays. So like I said, you can use it for various purposes when you want your data to speak to you, right? Another interesting kind of plot is called a swarm plot, very beautiful. This is again, but in this case, you can see that you do not have the categorization. It's doing it for the whole data set. It's basically showing you the day and the different, it's basically showing, but again, you have the left, right, for male and female, and it's basically showing you how your points are distributed, okay? You can actually see ad hoc. Another important plot for your thing are what are called palettes, which are the colors you're using. You could use different palettes. For example, here I use another one. Another very interesting plot to use is what is called a heat map. A heat map is, okay, oh God, we've got to use another data set. I did not, where is that data set? I think I missed it. This is a data set on car crashes. So it's not plotting that, but I can plot it instead here. Okay, here is then this one. Okay, it's not defined. Let me instead here.
DF का तो crash डाल
Yeah,
DF is defined.
No, I'll put this one. What is this one called? Tips underscore DF. Let me put tips underscore DF. Right. Okay. So I'm taking the tips. Oh, 1 minute. This. Okay. It has a problem with this. It's okay. We will get on to it. I'll just check it later on. You could also have a cluster map. It won't do this. It won't, because this is with another data set. Okay. So I will stop with this. Okay. I will leave it to you all to try off other things in your in this notebook. We are kind of tight on time, and Sir is already wanting me to stop. So I'm going to stop with my 1 hour. I'll give him the other half an hour, and I'll stop my share. But please go through different things on these notebooks, and if and when you have questions, we'll answer them. So Ashwin is asking me, is the rug plot similar to the distribution? So all of them have different purposes. Like I showed you, the rug plot very nicely shows you the density of the points, how well they are distributed. But the distribution plots, depending on whether you're using box or you're using violin, etc., they convey slightly different things. So just have a look at the plot so that you get convinced about what does it convey. You can share, Najim. Are you sharing your screen? Share your screen.
Should I share mine?
Yeah, I'm sure. Yeah, so I'll hand it over to Sir, and you can add your questions on Slack also, in case they don't get answered now. Yeah. So in continuation to.
Yeah, so in continuation to
Okay, okay, sorry.
this is just in continuation of what Priya did and little bit of statistics which you have done earlier and now. Yeah, so basically we'll see statistics and visualization together in this presentation. So there's this notebook which has been shared with you, which is called Essential Statistics. It is there on the GitHub page with you. And this notebook is just a recap of descriptive statistics which you have done, data visualization, some basic probability basics, and various distributions which we have, and so on. Okay, so the required libraries are NumPy, Pandas, Matplotlib, Seaborn, SciPy, Jupyter, right? So, like you have been told earlier, you can open this essential statistics and run it. And if you are getting an error with any of the commands, you have to uncomment this one and run this pip install numpy. So in one go, I am installing all these things, right? I can be doing it, say cpip install, and so if you are connected to the net, you will see that it will get installed. In my case, it says requirement already satisfied. So NumPy is already there, right? So this pip install is a great thing. Whenever a certain library is not installed, you can do it using pip. So in this command which we have on this line, it installs NumPy, Pandas, Matplotlib, Seaborn, SciPy, Jupyter, all in one go. Okay. And as you see now, I'm importing NumPy as NP. I am importing Pandas as PD, importing matplotlib.pyplot as PLT, and importing Seaborn as SNS. From SciPy import stats. I hope you understand what these cryptic things mean. I'll just add a few columns here to show what we basically do in Python. This is for people who are working with Python for the first time. See, for example, these things, they act, Python acts like a calculator. Here I have 23 plus 89 and it is giving me an answer, right? If I change the plus to minus or a star, it will give me subtraction, or star will give me multiplication, and 2 stars will give me to the power of 23 to the power of 89. Okay. So now suppose I want to do sine, when it can do so much of math, and I try to do sine of 23, you will get an error here. You see, you getting error because it doesn't know what sine is. So what is done is you import math as m. That's why we are importing math here. And now when I say m dot sine 23, you will get the value, right? So in this way, this package, this library maths which we have, we are giving it an alias m. And whenever I say m dot sine, m dot cos, I will get those functions. Okay. Another thing you can notice is if I do m dot and use the tab, I get all the functions which are there, which are possible. Ceil, comb, copy sign, cost, cos hyperbolic, right? And so on and so forth. So all these functions which are defined in math package, which I'm now aliasing it to M, are given here. Okay. So this is the power of Python. And instead of having all those libraries running at the same time and making your system slow, you just import time to time, whichever libraries which you are using. So here we'll be using NumPy. Similarly, as we saw in math, similarly in NumPy also, once I run this import NumPy as NP, NumPy also has sign. So this function sign is not defined not only in math, but also in NumPy. It is there in SciPy. It is there in various packages. So some functions you may use from one or the other, or from, right? So these are the ones which we'll be using. And from SciPy, we are using stats, right? So stats will do a statistics. So look at this. I have a variable called data, and I'm storing all these numbers, 23, 45. This whole list is being stored in this variable called data, right? So 23, 45, 58, 76, so on and so forth. So when you have just numbers sitting looking at you, you don't make sense of the whole thing. To understand when you have a set of numbers, what they are signifying, you have to either arrange them in ascending order, descending order. You have to find the mean of that. You have to find variance and various things. And once you do that, you can understand what the data set is. So you have seen np.read underscore CSV from a file. But here in this example, what we are looking at is I've artificially created some numbers and I'm trying to look at what this data set is. And I have some basic statistics which will give me some idea of what it is. So if I run this block, you will see that it is printing me mean is 51.529, median is 56, mode is 56, around count 3. Standard deviation is 25. Variance, which is square of standard deviation, is 631.66. Minimum is 12. Maximum is 90. 25th percentile is 34 and 75 percentile. So you see on top, np.mean of the data is giving us the mean. So it is basically mean. What is mean? You add up all the numbers and divide it by the number of numbers which are there, which are 1, 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 17 numbers. So 23 plus 45 plus 56, we have added all of them and divided by 17. So that gives you the mean. Median gives you the middlemost value. That is, if you arrange them in ascending or descending order, the middlemost point is what mean gives you. A median gives you. Mean is the average, the normal average. So there are 3 types of averages: mean, median, and mode. Mean is the usual average which we talk about, adding all of them and dividing it by the number of entries. Median gives you the middlemost value. Mode gives you the most frequently occurring number, right? So there are 3 different averages which are used by people for different things. Fashion designers, when they are making clothes, they use mode. The medians are used for most frequently occurring things. And standard deviation gives you an idea of how the data is deviated around the central position, the mean value. So what you do is you find the average mean, you subtract each value from the mean, You take the average of that and take the root. That gives you the standard deviation. But when you are using this from SciPy, we are using these stats, or from NumPy. NumPy, when you say np.std data, it is giving you this standard deviation, right? Similarly, np.var is giving us the variance, how the data is varying. np.min gives you the minimum of that, which is 12, and np.max gives you 90. So once you do statistics with data, then you get an idea of what it is. We know what is the least value, what is the maximum value. We know what is the average value, which is the middlemost value, and so on. Below these two, you can see another 25th percentile and 75th percentile. So 34 is 25th percentile. Basically, this 25th percentile is also called quartile 1. Quartile 2 is median, and quartile 3 is 75. So 25th percentile, which is Q1, is basically where is the 25% of data lying, right? It is the mark where below that mark, 25% data is lying below that. Okay. Median is the middlemost value, which shows you 50% is data is lying below it, 50% is above it. And 75th percentile gives you, which is the mark where 75% of data points are lying and 25% are lying on the right of it, beyond it, right? So these are the Q1, Q2, and Q3. And Priya mentioned to you about the outliers. There are certain values which you realize are outliers, and an outlier they can be spurious points which are not required. They are very oddballs, or they can be very interesting objects. So it is very important to find out these outliers. And in the box plots which we Priya did, you must have seen those dots, and we'll come to it as we proceed ahead. Right? So it is as simple as that. NP, we are using NumPy np.mean to find the mean of this data. np.median gives you the median, np.mode, and so on. And when you want to find out the percentiles, data, 25 will give you the 25th percent. In fact, I can even write another line here, which is a print and the middlemost point, which is the 50th percentile, which basically you will realize is nothing but median value. We can compare it on top and see that is the median value. And how do we get that percentile? We do np dot percentile for what data set? This data, comma 50, and one more bracket to close the print statements. And what we are seeing is 56 is the 50th one, and you see it is agreeing with the same thing which we got from np.median, right? So quartile 1, quartile 2, quartile 3. So this is basically Q1. This is Q2, and this is Q3. And here it is. What is important to also note is the interquartile range. Interquartile range is Q3 minus Q1, right? What we have, this is our interquartile range. I'll change this to, yeah. So this gives you the interquartile range, this value. Yeah, so this defines what is interquartile range, and the outliers which we see are, it is, if you take Q1 and subtract from it 1.5 into the interquartile range, this will give you the lowermost outliers, and the other one is Q3 plus 1.5 of the interquartile range. Yeah, so these two things, they define you the range which defines as the um, outliers. Yeah, so this is important. And here is the data visualization. Again, we are using the Matplotlib and PLT figured. You can define the figure size, which is 8, 5. You can play around with this and change the sizes and see that if I change this to, this is 8, 5. If I made it say 18, 5, you see that thing is becoming as big, right? So you can change the figure size by this command here. And PLT hist will give you the histogram of this data which we have. And we define the bins as 5, or you can make bins as say 15 bins. That is, it's making blocks of 15 and doing it. And you can change the color. Here it is sky blue. There are different palettes where you can change the colors, and you see you can change, sorry, the B went. You see you can change the colors of this, and the edge colors is black or whatever you change. Okay. You can set titles, you can set X label, you can set Y label, and you can show it. Similarly, you have this box plot where we get the box plot. And what this is giving is, this line is giving you the median, the middle one, Q2. This line gives you Q3. This line gives you Q1. And these are the lines which are defining the, so the interquartile ranges from Q3 to Q. This is the range. And 1.5 plus Q3 is giving you the outlier point, any points before that, and when, yeah, and any point below this, yeah. So these give you the outliers, things lying beyond these two lines. Okay. So similarly, you have some basic. Do we have?
He's saying
1 more minute. Yeah. Okay. So in 1 minute, I'll wind up, then we'll have some questions. So here we have probability basics. I have outcomes, heads and tails, and I have probabilities. Suppose they are 0.4, 4 out of 10 I've got heads, and 6 out of 10 I've got tails. And I do the figure with PLT bar outcomes probability and set different colors. I get blue and red. Yeah. So if you can change these to say 5 and 5, you will get that the probabilities are same and so on, right? So this gives you the, and we can set the limits, Y limit and Y label and X label and various things here. Similarly, you have these PLT normal distributions. Somebody had asked, how do you get random points? We are using np.random. In this case, I'm using np random.normal. So it is giving me a random distribution of points in a normal Gaussian distribution. So if you don't want normal, if you want some other default, or there are different distributions, exponent, binomial distribution, or you can change that and you'll get this. So here we are plotting this whole thing. And you can control the color by setting the color. You can say what the data is distributed. The data is distributed in the bar plot. And this normal density plot is also being plotted here, right? some things which Priya has shown. And similarly, we have here correlation. If you have two variables in data, and which I have created here. One is by NP-seed, I have created X, 50 values, and Y is some kind of a X into 2 plus X value, and it is creating another one and trying to find whether there is a correlation between them. Whether as X changes, will Y also change? And what we are seeing here is some kind of a relationship, right? So we are having a scatter plot, and we are using NP dot core coefficient for XY between 0, 1, and getting what is the correlation coefficient. So it's giving you 0.99. Yeah, Pearson's correlation is 0.9. So it's very well correlated. Correlation lies between 0 to 1. 0 showing no correlation between the two, no relation between them. 1 showing a very good relation. And 0 to -1 give you negative relation, where if one increases, the other decreases. Right? We'll come to these hypothesis testing and other things later. These are very important for us to know in statistics, which are used in astronomy. Like, for example, t-test and f-test and regression. But what I will do is I'll stop for today. And in the next session, when we have, it is very essential that we understand what regression is. Regression is you find a relation between one or two or one or many variables, and you try to spit a linear relation between them, or other kind of curves to show what kind of a relation lies between them. So with this, I will stop. So you run the first part of the notebook which has been shared with you, change parameters, change things, and run it and see. And you will see that these two link up. So what Priya has done in Matplotlib and Seaborn, here we are doing it with some data, and we are playing around with the statistics of the data. Yeah. So I'll stop with this, and if there are some questions, we'll answer.
So tell people they're free to unmute, right? Yeah, so people can actually unmute themselves or list the thing. Ashutosh is asking me when will we be allotted the capstone project. So I'm not too sure about it. Daniel maybe can answer that. I think you'll be
Yeah, so we're
informed.
going to share resources later this week in the Slack on how to proceed with it. Yeah, so we're not going to allocate. So people will have to do it by themselves. You have to get a data by yourself and work and use what you have learned in this training to make a presentation, do analysis, collect data, analyze your data, and make presentation. So the guidelines for how to do that will be shared later this week. Thank you.
Okay. Yeah. Any other questions? Sorry, we pushed in a lot of things into this thing, but there is a lot. So please try the notebooks and try running things. In case you get stuck, we are anyway there on Slack, so you can let us know, and we'd be happy to answer your questions. Yeah, let me just check if there are other questions. No, there's nothing over there.
Yeah, someone said, can you explain when to use different types of plots and in what scenarios?
So different kinds of plots, which kind of plots?
You're saying, can you explain when to use different types of plots and in what scenarios?
Okay, you want to answer that, Smriti Mishra? Can you explain when to use different kinds of plots and in what scenarios? So like I said, your plot is going to convey a certain thing, right? So depending upon what you wanted to convey and highlight, you need to select. Okay, he wants the re-highlight briefly on interquartile range. Okay.
So
Quartile, like I said, if you have data, if you just have numbers, it doesn't make sense. So you arrange them in a certain order.
Ascending order.
One certain order, ascending or descending. Generally, you do it in an ascending order. The lesser values on one, say you start off with, and higher values on top. Okay. And the middlemost value, suppose I have 3, 7, 6, 9, and 5. The middlemost value is your median. It is the quartile 50. That's the mark where half the 2 points are lying on the left, 2 on the right. Or if they are 100 points, 50 are here, and 49.5 here, 49.5 here. That's the median value. Quartile 1 is the point where 25% of points are lying below, and quartile 3 is the 25% of points are lying above it, or 75% are lying below it. Okay. So Q1 is the middlemost point.
No, Q2 is
Q2 is the middlemost point. Q1 is where 25% are on the left. Q3 are which 25% on the right of it. So this difference between Q3 and Q1 is called the interquartile range. And this is important for us to define the outliers. So outliers are defined as 1.5 times the interquartile range, that is the difference between Q3 minus Q1, and you subtract it from Q1. And things lying beyond that point are the outliers. For example, if we have conducted an exam and most of you have got around, say, 85, 88, 89, 92, 93, 79, 78, and so on. But there is one person who suddenly has got, say, 15 marks. He or she is an outlier. So what happens with these outliers is it changes the value of mean tremendously. So these are bad points. Sometimes they are bad points, they are spurious points. You have a star cluster and suddenly you find a very bright object in that. And all the magnitudes, all the brightness for most of the stars are lying within a certain range. And one is extremely faint or extremely bright. So then if it is extremely faint, you may say that this star doesn't belong to this cluster. It is very, very far off somewhere. Or if it's something bright, you can say it is some kind of a foreground star, or it is something else, right? So these outliers are found using this interquartile range, and subtracting 1.5 times interquartile range from Q1 to give the outliers below the lower ones, and Q3 plus 1.5 times interquartile range will give you the extreme values on the right. I hope it's clear.
Yeah.
And these outliers can be bad points or can be very interesting objects. So you should not just throw them out blindly, but you have to look at them a bit more seriously when you are working with outliers.
Yeah, okay. Thank you for the clarification.
Anything else? See, important thing which we shall do is I'll take some time to do T tests, F tests, and various tests which are important, which we will do in other sessions.
Yeah,
Okay.
and for the last minute, I'm very sorry, but I wanted to specify that even for Seaborn as well as for Matplotlib, there are what are called galleries. Okay, so for example, if you go to Seaborn, you can see the Seaborn gallery right here. And for example, if you see the Seaborn gallery, it is very useful to use that to actually find the kind of plot you want. 1 minute, where is the Seaborn gallery? See, come on. Similarly, you'll get a Matplotlib gallery also, and you can actually use, I'm sorry, but to actually choose the kind of plot you want. And if you look at this, for example, I wanted to mention this. For example, there's a plot of your choice. You would like a plot of this kind. For example, violin plot, which we were already talking about. You'll click on this, and here you can find the complete code for this plot, right? So once you understand how this code is written, you can tailor make it for your use, right? So it's very, very useful to use these galleries. There is some similar gallery like this even for Matplotlib. So you can actually look at the plots and see what kind of a plot you want, right? And accordingly choose this thing. For example, this or whatever plot you want, choose it from this. Yeah, that's it. Thank you. Daniel, Libo, do we stop now or?
Oh, yes, we can end the section now and then we'll reconvene in the evening.
Libo or Daniel?
Yeah, can you hear me?
I can't hear.
Yeah, I get you. Yeah.
Okay, cool. So we can end this section now and catch up in the evening, same time, 6 p.m. South African time. So
Okay.
thanks for joining this morning. It's going to be the same presentation. This is just the second section today. We target people in the western part of the world. So it's not going to be different from the presentation. Please go to the GitHub repo and go through the
we'll
notes.
exit.
Also self-explanatory and also get your hands dirty. Thank you, everyone.
We'll exit.
Okay. Bye-bye.
Bye-bye.